So we will see today what is Huffman coding and how can we implement it using binary trees and priority queue. So before diving deep into what exactly is Huffman, we will see why it is necessary and why we are needed to create this video. So what is the problem statement? The problem statement is that while we use our ASCII encoding for any messages or etc., each character uses a fixed 1 bit size, which is the memory needed for our character. Even though some appear more often than other, we does not consider this in our fact, and that wastes so much of our space. So what Huffman exactly does is it optimizes the storage by using shorter codes for frequently appeared character, like in a sentence the character that occur more often, we assign it shorter values, and that reduces the file size and improvises our compression efficiency. What it exactly does and how it exactly does, we will see after. So, what is Huffman? Huffman coding was proposed by Dr. David A. Huffman in the year 1952, and some describe it as a method for construction of minimum redundancy codes. It is widely used in data compression and transmission. It is very much used in text file compression and message encryption. We can encrypt our message in one side, and then we can use a decryptor on the other side to decrypt the message. So it is also kind of secret messaging. So how does the algorithm helps to solve the problem? The Huffman is dynamic, unlike the fixed length encoding in the ASCII. What ASCII does is it represents in the binary value and assigns that and then again decrypt that. However, in the variable length encoding, frequently used characters are assigned shorter codes, improving our efficiency. What exactly are the procedures? So first of all, we scan the text that is to be compressed, and we make a kind of table for tallying occurrences of all the characters. Next step, we sort and prioritize each characters based on the number of occurrences, that is the number of the frequency basis. We sort them and make a kind of table. Then we build Hoffman code tree based on that prioritized list or frequency table. We perform a traversal for the tree to determine all the code words that is necessary. We then again scan the text and create new file using the Huffman codes. For example, we have taken here a random text generated by AI that reads airy eyes seen near lake. What we do now is we count the occurrences of all the characters in the text. We took our text here. So what characters are present here? We sort them E, E, R, I, space. Yeah, space is also considered Y, S, N, A, R, L, and K, and a dot. What is the frequency of each character in the text? So what is the frequency? From the very basics, we know that these are the occurrences like character, capital E is repeated once, small e 8 times, R 2 times, small I 1 time, space 4, Y1, S2, N2, A2, L 1 time, K 1 time, and a full stop 1 time. Now we have to build a tree. To build a tree, at first we create a min-if or priority queue. Here each node represents a character and its frequency, and the node with smallest frequency has the highest priority from um, priority queue. Here is our priority queue with our characters and frequencies. Now, um, first we create a new node, dequeue node with node one node and make it left subtree, and again we dequeue a next node with lowest frequency and make it right subtree. Then we add the frequency of two nodes and make new node with the sum of frequencies of two smaller nodes. Then again we enqueue new node back to the queue. Here is a visual representation. This is we dequeue two elements or two characters E and I and make a binary tree.
Here is the sum of frequencies of E and I, which is 2, and we enqueue this again in priority queue like this. And now we select two other characters with lowest frequencies. Let's say Y and L having 1 frequencies, and we again make another subtree, hmm, with a new node and having frequency 2, and again we enqueue this into a priority key. So now our priority key queue becomes um, a queue with 2 1 1 frequency with k and dot, and here are our new nodes 2 and 2, which are the combination of E, I and YL. Now again we dequeue k and full stop, so that we make another new node and enqueue into the priority queue. So here is the new node that we are going to enqueue again in the priority queue like this.
After the construction of priority queue, the elements with highest priority are dequeued. The elements with highest priority are now R and S. They are dequeued and made into a separate tree, like so. And the combined priority of R and S tree is 4. Now 4 is enqueued according to its priority into the priority queue. And then elements with highest priority now are N and A. The elements are then dequeued and made into a separate tree. Then they are again enqueued according to their priority. They are enqueued in the fourth, fifth, sixth position. And then now the elements with highest priority are E, I, and Y and L. They are dequeued and made into a separate tree. They are again enqueued according to their priority. After enqueuing them, uh, the now highest priority elements are SP with 4, KI with 2. Now they are made into a separate tree with priority 6, and it is then enqueued according to its priority.
After this point, the two nodes with the lowest frequency are picked. Here the three nodes, that is first, second, and third, that is index 0, 1, and 2 have same frequency, that is 4. So let us pick first two nodes and combine them, which makes its frequency 8. Now, after creating this, we again insert this node into the main heap or priority queue. After that, we see that there is frequency 4, 6, 8, and again another 8. Now again, the two frequencies which are lowest, that is 4 and 6, are again picked up and then combined. The recombined frequency ultimately becomes 10. Now this recombined frequency is again inserted or enqueued into the priority queue, which makes it 8, 8, and 10. Now we have three frequencies of which two are same, that is 8 and 8. Now again, the two frequencies, that is 8 and 8, which are minimum, are picked and then recombined, which ultimately makes it 16. Now again, the recombined node is inserted inside the minimum heap queue, which makes it 10 and 16. Now, now seeing this, we see that there are two nodes 10 and 16. The minimum frequency of these two nodes is 10. So the lowest frequency is 10. However, we have only two nodes left, so we must have to reconcile them, and after recombining them, their both frequency become 26. Now at this point, our tree is completed. Now after enqueuing this node, there is only one node left in the priority queue. So finally our tree is built in this process.
For Hoffman encoding, first of all, we need a Hoffman tree. And how can a Hoffman tree be made? So, a Hoffman tree can be made by using a data structure, for example, an array. So, from an array, we can take two values with smaller frequencies and then make a tree out of it. And then we insert it back into the array, and then we take out another two elements. So, and then the process goes on like that, and we get a Hoffman tree. And in that Hoffman tree, the characteristic of a Hoffman tree is that as we move to the left branch, we assign it 0, and as we move to the right branch, we assign it 1. So for the leftmost element, we get zeros, only zeros, and as we move to the rightmost side of the tree, we get only 1. So for example, in our case, the example that we have taken, uh, the leftmost side has a character E. So it has been assigned 0000, which means it is on the leftmost side. We travel 4 times in that branch, and then we get E. And in the rightmost side we have A. So we travel 4 times in the rightmost side and we get A. Okay, and in Hoffman encoding, we have got total 73 bits of information in our example. So if we have used ASCII value, then it would have taken 8 into 26 equals to 208 bits, because 26 is the total number of letters that appear in our text. So the whole message would be have 208 bits. And if we have acted smarter and used, since uh, there are total 13 characters which are repeated 26 times, so if we have assigned a 4-bit value to every character, then what we have got is 26 into 4, that is equals to 104 bits. So we would have gotten 104 bits of information, but still Hoffman encoding is good because it takes only 73 bits. So how can it be decoded? If I am the receiver and I receive a Hoffman encoded message which is 0110, something like that, then how can I decode it? So for decoding it, I must have a Hoffman tree, the same Hoffman tree that the sender has, because only then I will be able to convert that message. So if I have that same tree, then what I will do is I will look at the tree and look at the message. The message says 0, then I will move to the left side. If the message says 1, I get to the right side, and eventually I will reach to a letter, and then that is the letter particular uh, which is conveyed in the message. So that is how I can decode it, and this is how Hoffman encoding and decoding is done. Thank you.